Hello students, welcome back to a new video lecture on Maxwell equation and electromagnetic waves. Today we are going to discuss about Gauss divergence theorem. So let us see what is the statement of this theorem. It states that if a closed surface S encloses a volume V in a vector field A, then the surface integral of the normal component of A over the entire surface S is equal to the volume integral of divergence A over the volume V enclosed by surface S. So this statement can be mathematically represented as a surface integral of A dot ds is equal to volume integral of divergence of S dot dv. So this is what exactly you can mathematically represent that. So next we are trying to prove this. This is a statement and mathematical equation. Let us try to show this. So let us try to prove this proof. So to prove this, let us consider a surface S which encloses a volume V in a vector field A. Okay, surface S encloses a volume V in a vector field A. Let the volume V will be divided into large number of small elemental volume. Let us say delta V1, delta V2, delta V3, so on, delta Vi. So this small elemental volume enclosing by a surface area, let us say delta S1, delta S2, delta S3, so on, delta Si, so it's a respective surface area I have denoted. Let's take now flux is passing through this surface S. So each of this volume or surface area, small elemental surface area, also a flux passing through that. So now let us consider outward flux as a positive quantity. Outward flux of the vector field through the closed surface is a positive, and inward flux as negative. So outward, let us say positive quantity, and inward, let us say negative quantity. Now just for understanding, this figure may not be necessary, just to understand what exactly we are talking. Let us consider a surface S which encloses a volume V. So this is a surface and which encloses a volume V. So this volume is divided into small elemental volume. So this is delta V1, delta V2, delta V3, so on, like this. Okay. So now let us say flux is entering from this side and leaving from this side, vector. So what happens is, if you carefully observe, let us consider first elemental volume delta V1. From one phase outward flux, that is from the delta V1 flux is coming out, the same flux is entering into inward for delta V2. So whatever coming out of the delta V1, that is entering into delta V2. So therefore the coming outward flux we say positive quantity and inward flux we say negative quantity. Then not only that, they are equal, so therefore they cancel each other. Therefore the outward flux from the small elements of volume will cancel out each other in each part. Delta V1 and V2 cancel, V2 V3 cancel, V3 V4 cancel, like that it's go on cancelling. Okay, so cancel out, but only those outer bounding surface will remain, except outer bounding surface it will remain, that is entering, leaving. The rest all cancel each other. So therefore you can write total outward flux through the closed surface S, that is surface integral of the vector over the surface S equal to sum of outward flux over the surfaces delta S1, S2, S3, so on. So therefore you can write the surface integral is equal to summation, it is sum of, again surface integral of each surfaces. So let us call this as equation 1. Okay, so sheet is complete. Take a fresh sheet. Okay, the value of divergence of A is in a small element like delta Vi having surface delta Si, delta Vi having surface delta Si, that can be given as divergence of A is equal to limit delta Vi tending to 0, then 1 by delta Vi surface integral of A dot S. Very important thing is limit, it is tending to 0. We made a volume as small as possible, or this can be written as surface integral A dot ds is equal to divergence A into delta Vi. Therefore sum of surface integral A dot ds is equal to sum of divergence A delta Vi. So this is for single, so now we have summed it. Okay, when delta Vi is equal to dV, that is an infinite number of small volume elements are involved and delta Vi is tending to 0, we can write summation divergence of A delta Vi is equal to volume integral div A into dV. Therefore I can write summation we have left here, so this is equal to summation surface integral is equal to volume integral divergence A into dV. Call this as equation 2. Now comparing equation 1 and 2, you can write surface integral A dot ds is equal to volume integral divergence A dV, or simply you can write it as del dot E. T, one and the same, div A or del dot E. So this is a required formula. This is a required formula. So therefore we have done the proof. So this gauss divergence theorem helps us to convert surface to volume integral, or we can write volume integral in terms of surface integral. So it's a vice versa. So it is an interconversion of surface to volume or volume to surface. So that's what exactly significance of gauss divergence theorem. Next, let us move on to another theorem, that is Stokes theorem. So Stokes theorem, there is no derivation for this, only a statement, that's all. It states that the surface integral of the curl of a vector A over a surface S of any shape is equal to the line integral of the vector field A over the boundary of that surface. So I will repeat. It states that the surface integral of the curl of a vector A over a surface S of any shape is equal to the line integral of vector field A over the boundary of that surface. So that is surface integral curl A dot ds is equal to line integral over a closed path A dot dl, or we can write it as del cross E, surface integral del cross A ds is equal to line integral over a closed path. Okay. So this theorem helps us to convert a line integral of a vector to surface integral, or surface to line integral, vice versa. So there is no derivation for this, just a statement. Okay. So let us move on to next concept, that is next theorem, that is Gauss theorem. This also, there is no derivation as such, it is just a statement. Law in electrostatics. This you have already seen in your PUC, all these things. Just we are recalling again, that's all. So let us see what is the statement of this. Okay. So Gauss theorem, or law in electrostatics, it states that total electric flux in free space through a closed surface equal to 1 by epsilon naught times the charge enclosed by the surface. So that can be mathematically written as phi E surface integral E dot ds is equal to Q by epsilon naught. So Q is the charge. So there is no derivation again. So one more law, these other things you have seen in PUC. Again we will see another one, that is Gauss law for magnetic fields. So this can be stated as magnetic flux line always from a closed loop in a magnetic field in case of the closed surface in a magnetic field, every line that enters the surface, there must always be a line emerging out of the surface. What is that? Flux, if it is entering, magnetic flux field line is entering the surface, there should be magnetic lines of force which is leaving the surface. So therefore, total flux over the closed surface is equal to 0. That is, phi is equal to integral B dot ds is equal to 0, or del dot B is equal to 0. So in other words, Gauss law for magnetic field says there is no source, simply divergence of magnetic field is 0, or it says there is no source or sink for the magnetic field. They form a closed loop. They form a closed loop. Example, you can take the solenoid. The solenoid is nothing but a coil. Coil is connected to battery, and current passes through the solenoid. It generates the magnetic field lines of force. So solenoid will become like a magnet, electromagnet. It will be electromagnet. From one end of the solenoid, that is, one end will act like a north pole, another end will act like a south pole, and magnetic lines of force emerging out of the north pole will converge at the south pole. That is what exactly Gauss law for magnetic field says. Next we will move on to very important law, that is Biot-Savart's law. Biot-Savart's law. Okay, so let us see what exactly it says and what are the things we have to discuss. Biot-Savart's law. So it's name of the scientist, Biot-Savart's law. So let us see the statement. So Biot-Savart's law says magnitude of the magnetic field dB is directly proportional to product of current, so inversely proportional to the square of the distance between current element at the point P. That's what it says. To understand this, I have to draw a figure and explain. Okay, so let us consider a conductor of arbitrary shape. So I'll a conductor which carries a steady current. So let us say this is a conductor of arbitrary shape. There is no shape as such, arbitrary shape conductor I will consider, which carries a steady current I. So current I is passing through this conductor. Okay, let us consider small element AB of length dl. So total length is dl. So let me consider a point P and the magnetic field produced by the current carrying conductor. So you have considered element. So now let me draw the tangent, and the amount of magnetic field produced at a point P, this point P, let's say dB is the amount of magnetic field produced. So angle between this line, let us say theta, and distance, let us say, let r be the distance, of the P from current element. So this small element will have current ideal, and theta be the angle between dl and r. So according to Biot-Savart's law, the magnitude of magnetic field dB is directly proportional to the product of ideal sine theta and inversely proportional to square of the distance between the current element and the point P. Thus we can write, so statement we can put it mathematically, dB is directly proportional to I dl sine theta and inversely proportional to dB is inversely proportional to square of the distance. So putting together dB is proportional to I dl sine theta divided by r square. So dB is equal to, replacing that proportionality constant with a k, so I dl sine theta divided by r square, where k is the constant of proportionality and its value for free space, that is for free space k is mu naught 4 pi, value of k. So therefore we can write this as mu naught 4 pi I dl sine theta divided by r square, that's equal to mu naught 4 pi I dl dot r divided by r cube. So this is nothing but Biot-Savart's law. This is what exactly Biot-Savart's law says. So this is what exactly Biot-Savart's law says. R square, you can write it as dB is equal to mu naught by 4 pi I dl dot r cube. With this we will conclude this video lecture. So let us discuss more about Ampere's law and other thing in next video lecture. Thank you.